We are live, sir. We can start.
Right. Good morning. And this is Foundations of Continuum Mechanics, live session 3. Today we'll be taking up discussion problems on the section on balance laws. So this is the third module in the fourth module in this course. The first one was on background mathematics. The second one was on stresses. The third on kinematics, which we discussed in the last session, and today will be on balance laws. And the live session 4, which will happen next week, we'll be taking up questions on constitutive models and everything else from the course, if any. So what I'll do is, as previously, I'll take you through the slides for this module, and then as and when we encounter a situation where there were questions on the question forum, I will slow down and discuss that. And today I'll also discuss a derivation which was asked on the forum. Some of you could not do it, so you wanted me to show that, so I'll show that as well. Right, so this session on this module on balance laws, it always starts from the discussion on the material derivative of elements. So we need to be able to write the derivative of line elements, area elements, and volume elements, because that is required when writing the balance laws. So I'll quickly take you through it. So for the material derivative of line element, what we are interested to do is to be able to write the time derivative of d small x, which is the vector, the length, the displacement vector in the spatial or the Eulerian coordinate system that's in the current configuration. So we want to write that in terms of d small x in the, we want to write d small x dot in terms of d small x. So that is straightforward. There was nothing special we got here. And we also wrote how to write we also saw how to write the material derivative of the dot product between two different displacements originating from the same point. Then what was new was the material derivative of area elements. So for that, we first wrote how to express the area element. Now the same d capital X and d capital X1 and d capital X2, they deform to d small x1 and d small x2, forming an area d gamma, which was d gamma not earlier. So we first try to express our d gamma in terms of d gamma not, and that comes expressed in terms of the Jacobian, that is the determinant of the deformation gradient tensor f. That's a very important quantity. And once we have done that, as you can see in equation C, we take the material derivative of that and we get the expression for the material derivative of d gamma in terms of d gamma. So that's the material derivative of the area element, and it is expressed, if you look at equation E, in terms of the velocity gradient tensor, that is L. Now there was a question here, if I go back, we had used an identity which says that the determinant of A, when we take the material derivative of that, can be written as a trace of material derivative of A dotted with A inverse times the determinant of A. So this identity was used in while applying the determinant, applying the material derivative to the determinant of F to obtain the expression for the material derivative of the Jacobian. That's a very important expression, because that is an expression we tend to use a lot, where we try to express the Jacobian, the derivative, that's material derivative of J, in terms of J. So this is something we'll see a lot of times. It's a very important identity, and there was a question on that in the forum. So what I'll do is I will show you how to get this. Let's write the identity first. So here, this dot that we have is the inner product between these matrices. So once you do that, you get a matrix again, and then we take the trace of that matrix, which comes out to be a scalar multiplied by this scalar determinant of A, that gives this scalar, which is the time rate change of the determinant of A. Let's solve this. So given that we had used this for the determinant of F, which is actually Jacobian, so we will call this determinant of A as Jacobian, which actually is the determinant of F. So in fact, I can replace this with an F. It'll just help me write things in a more compact fashion, avoiding writing determinant of F again and again. So what we'll do is we'll start from the expression for the determinant of F, which is the Jacobian. So if I use the initial notation, then I can write this as the permutation symbol epsilon ijk, and then I use the form where I have f I1, f J2, and f K3. So that's the initial notation representation of the determinant of a tensor F, or a matrix F. So now what we do is, in the left hand side, we have to write the d by dt of this expression. And remember, epsilon is simply constant. So it does not change with time. So I can take this out of the derivative. So what I have is in this case, what I have is I have three different columns of f, that is fi1, fj2, and fk3. So the d by dt actually is, I can apply the product rule here. So this becomes d by dt of this expression, which is actually what we are writing as j dot. So this becomes equal to, we don't need to write that, we just write it here. That's epsilon ijk times f I1 with a dot on top, and then we have fj2 and fk3. Let's keep this epsilon outside, and then similarly we have, from the product rule, we have fi1, fj2 with a dot on top, fk3, and thirdly we have fi1, fj2 times fk3 with a time derivative on it, right? So this is the expression that we have. Now what we do is we write this, the expressions that we have here, in terms of, let's look at these ones. So we'll try to express them in terms of the cofactor of a matrix. So let me show you what that is. So if I write the matrix F, so this matrix has 9 cofactors. So the way we write a cofactor is if I write C11, so that is if I take this 1 element and freeze the rows and columns there, so whatever I am left with forms my minor matrix, and the cofactor is simply in this case 1 plus 1 to the power minus 1, and then we have the minor 1 which basically is 1 plus 1 to the power minus 1. So these ones and this 1 and 1 are the indices that we have in this C, and then the minor is simply this matrix F22, F23, F32, and F33. And this is typically what we use in calculating the determinant or in writing the inverse. So this is something we had discussed earlier in the course. So this is, so I can write in general, I can write the I comma jth cofactor as I plus j to the power of minus 1 times the minor ij, right? So that's my cofactor in this case, the cofactor matrix. And we also use this cofactor in terms of the determinant of that. So sometimes when we say cofactor, then we may express that as the determinant as well. But for now, let's call it the cofactor matrix. Right, so let's clean things a bit. So I'll show you why we are discussing this idea of the cofactor matrix. So let's try to write CI1. And let me give an expression first, and then we'll see what it is. So CI1 is epsilon ijk, aj2, and ak3. So let's expand this expression and see what we have here. So if I try to show this for C, if I put I equal to 1 here, then what we get is we get C11 equals epsilon 1jk aj2 and ak3. Let's expand this. So because we already have an epsilon 1 here, then we only get 2 terms here which are non-zero if I expand this using summation rule on j and k. So this becomes epsilon 1 and j is 2 and k is 3. So we get a22, a3. Let me check. Yeah. And then we have another term, which is epsilon, and then j is 3 and k is 2. So I get A32 times A23, right? Sorry, I've started using A here now. I should be using F. This is FJ2 and this is FK3. Right. So let's simplify this. So we have epsilon 1, 2, 3. That's a 1. So this is F22, F33, and epsilon 1, 3, 2 is minus 1. This is minus F32 and F23. Right, so this is what we have for C11. Now, if I go back to the cofactor matrix, although I don't have to use the expression for the minor here, because I can easily see. So if you allow me to freeze this and this, then the determinant of this matrix that we have, which is indeed the minor matrix, but since we have index 1, 1 here, so this I plus j to the minus 1 in this case is did I do a mistake? Oh, so, I'm sorry, this is minus 1 to the power I plus j. Excuse me for that. So we have minus 1 to the power 1 plus 1, which is 2. So that's minus 1 to the power 2 is 1. So basically, this is simply the determinant of this matrix, which is what we have got here. F22 times F33 minus F32 times F23. So what we are seeing here is that although I was writing the matrix here, but this is the cofactor determinant. So let's use a tilde on top of this just to differentiate the matrix with the determinant. So this cofactor determinant can be written using this expression. I can also write F CJ2 as epsilon ijk, and this time we have Fk3 times Fi1, and similarly I can write Ck3, the cofactor determinant for kth row and the third column. Basically, this column here, if you take the different terms and the corresponding cofactor matrix and take the determinant of that, that can be expressed as epsilon ijk times Fi1 and Fj2. Again, you know the definition of the cofactor matrix. So it's not that difficult to see what the determinant of that would be. So it's a 2D matrix. So we have we sort of fix one of the indices of the epsilon once we have chosen which element we want to use for calculating the cofactor. But in general, if I just choose the ith row, first column, jth row, second column, or kth row, third column, then we get this expression. You can expand it and see what it will give the right thing. So this, once we have these expressions, then if I substitute these back into my LHS where I parked the expression and continued with the discussion on cofactors, let's continue the discussion. So my LHS now becomes, we have an epsilon ijk that we had here, and then we had, let's say we had an fi1 dot, and then we had fj2 fk3. So that's the first term if I've opened the brackets. Now let's look at this term. So that's epsilon ijk fj2 fk3. So if you look at this, let's number these cofactor determinant equations. Let's call them 1, 2, and 3. So this is simply the use of 1. You can see that. And then the second term is epsilon, sorry, I keep the fj2 dot out, and then I have epsilon ijk fi1 fk3. Let's look at this term, and this is exactly what we have in equation 2. So we use 2 here, and then the third one is fk3 dot, then we have epsilon ijk, and then fi1 and fj2. Right, so this is exactly what we have in equation 3, expression 3, fi1 fj2. So that's where we say use 3. So this becomes f dot i1 times c i1 plus f dot j2 c j2 and f dot k3 times c k3. Right. So this is the expression that we have, and then this can actually be further simplified to write f dot. We have an I, j, and k. So let's because I, j, and k are in the 3 terms are repeated. Let's call them with the new index m, just for convenience, and we'll call this m n and c m n. You can expand it and see, if you expand this over n, then this becomes f dot m1 times f dot sorry, c m1. That's the first expression, first term. Then we have f dot m2 times cm2. That's the second term, and so on. So we have very compactly been able to write our LHS as f dot mn times cmn. That's the beauty of indicial notation. It allows us to write things quite compactly. Now, what I'll do is, now I'm sure you are used to writing the determinant in terms of the adjoint. So if you remember, what you would have done is, if you had the matrix like this, and you had to calculate the inverse of the matrix. So one way was that first you would calculate the matrix C transpose, which is simply, I mean, first what we do is we calculate the cofactor determinant for each element, and then so that is what we'll call C11, C12, C13, C21, C22, C23, C31, C32, and C33. So this is something we calculate first, where we calculate the cofactor determinant corresponding to each element, and we form a matrix out of it, right? And then we would write the inverse as, so we'll divide this by determinant, so that becomes 1 by determinant of f. We do that, and then we take the transpose of this whole thing, and this is what we call f inverse. Right. So I'm sure you have done this in the past while studying matrices, so I'm not going into detail of that. So this matrix, which we call C transpose, this part is called, if you allow me to write this as determinant of f times f inverse, the C transpose is called the adjoint of the matrix F. And these are known ideas. We don't have to go into too much detail of that, but one of you had questions about it. So this is that C transpose that we have here. So what we are doing here is that we have been able to write the LHS as f dot mn times cmn, which is where cmn is the C matrix that we have. So I could write cmn as determinant of f, which is the Jacobian, times f inverse. So this is your C transpose actually is determinant of f times f inverse. And if I want to write this in the indicial notation, what I do is I write C transpose nm as j of f inverse nm. What we are saying is that the nm element of C transpose is, j is just a scalar, so j times the nm element of the matrix F inverse. So then this basically means that this is Cmn, which is j times F inverse nm. So this is what I was looking for, because I'll substitute this. Let's call this B and call this A. So I can substitute my B in A now. So this gives the LHS as Fmn. Sorry, there was a dot here. Yeah, there's a dot on F. And then the Cmn can now be written as a j times, and j I'll move here, j is a scalar, times F inverse Nm. All right. We're getting there now. Now the LHS is j times. Now if I look at F, this Mn and Nm, so it's easily, you can see that there's a dot product between these two. So it's an inner product. So I can write this as F dot dotted with an F inverse. But you also have mm. So this mm basically means that it's the trace of this. So this is that step where one has to go from the initial to the symbolic notation. So these are basically, if I look at the initial representation, these are two matrices being multiplied. It's inner product of that. And whatever I get, we have an mm component. I mean, if these, the first m and the second m, they were different, you would get a matrix. But actually, since if you look at this expression f dot mn times f inverse nm, it's a scalar because there is no free index here. So there is an mm component of the resultant matrix, which basically means that you are taking the trace of the matrix. So that's a trace of the resultant of f dot dotted with an f inverse. And that's it. We have shown that. Now left hand side, remember, was j dot. Get started. Let's go back up. We had started with a d by dt. Sorry, here. So the LHS here was the d by dt, that's the dot on the top of the determinant of f, which is the Jacobian. So this was j dot. So j dot can be written as j times the, let's write the way we had written, the trace of the time derivative, material derivative of f dotted with f inverse, that's the inner product, times j. If I write in terms of the definition of j, so that's the determinant of f dot is the trace of f dot dotted with an f inverse times a determinant of f. So this is exactly what we had to show, and we have shown this. Right, so let's move back to the discussion. So we have now proved this identity, and this is what we used to then show that the time derivative or the material derivative of the area element d gamma can be written in terms of d gamma. And then we moved on to the volume element, where we showed first that there is a relationship between d omega and d omega naught, which is what we showed here, which is through the Jacobian. And then we discussed that this Jacobian is, we had already seen this expression earlier when we talked about finite deformations in terms of the determinant of C, which is nothing but the square of the Jacobian in this case. So it's the same as what we had got earlier. We talked about isocoric motion where Jacobian is 1. And we also talked about the condition for isocoric motion where we have um, the divergence of velocity field is 0 if we have things changing over time. It's a continuous deformation. Then we can write the condition for isocoric motion as the divergence of velocity field. So that results in isocoric motion, also known as incompressible flow, as we discuss in the next slide. Right, so let's move on to lecture 47. So in lecture number 47, we talked about the derivation of the Reynolds transport theorem or the transport equation and the conservation of mass, that is the application of the transport theorem. So I'll not go into detail of the derivation again, but in transport theorem, what we do is we try to write the material derivative that we have here. Here is what you have the material derivative of the integral over an Eulerian quantity. So what this transport theorem allows us is to write the material derivative of some sort of a P star, which is the corresponding intensive quantity corresponding to a P. So let's have a look here. So let's look at the final theorem. Which is the boxed expression here. So now you can see that d by dt of the extensive quantity P is written as integral over the volume times d by dt of P star. So we have been able to move the d by dt, the material derivative, on the starred quantity, that is the intensive quantity. Okay, so that's the whole idea of the Reynolds transport theorem. Because for extensive quantity, this is just the time rate change of that. But when we write that in terms of the integral over intensive quantity, then we must know how to move the derivative on the P star. So you can see that here. So that's your d by dt of P written as integral of del by dt del t of P star. So we just expanded using some theorems. And this is what we call the Reynolds transport theorem. And this now can be applied to any quantity like mass, momentum, or energy. So if I apply it to mass, basically we have to choose what is our extensive quantity and what is the corresponding intensive quantity. So for mass, the extensive quantity is mass, and intensive quantity, because we're talking of things in per unit volume, so that becomes density. Let's show that. So in conservation of mass, when we apply this, because remember there's a conservation law that we have to start with. So the conservation law we have is that for a set of material particles, the mass does not change. That's conservation of mass. So if you decide on a set of material particles, then over time their mass will not change. So this means that d by dt of the extensive quantity m in this case is 0. So that's your actual equation. And then when we write that using the transport theorem, then we get del by del t, or sorry, d by dt over the intensive quantity. Let's go back and show you the expression. So we're using the form A of the transport theorem, where I have a d by dt of this and a vk comma k. So we apply that, and then that results in this form of the conservation of mass equation written in the Eulerian form. So that's the whole aim, that if you want to write things in the Eulerian form, that is when you use the Reynolds transport theorem. So this gives different forms of the equation. And then if you have incompressible fluids, or a flow situation where the flow can be assumed to be incompressible, then the material derivative of rho is 0. Remember, it's the material derivative. That's again a key point which is confusing. So if you take a material particle and you say that it is incompressible, so what that means is that its volume is not changing. If the volume of a given material particle does not change, and by definition the mass will not change, the mass is fixed for a material particle, that means the density is fixed. So that means that the material derivative of the density of that particle is zero. So rho dot is zero. So if you use in the correct form of the equation, which is B here, then all you get is Vk comma k times rho is zero. And since rho is not a zero quantity, so Vk comma k is zero, which results in the divergence of velocity field being zero. And this is exactly what we had gotten earlier as well for isocoric motion, which is nothing but incompressible flow, because isocoric situation means that the volume of an element does not change, which is basically the same thing as incompressible. Then we talked about the conservation of mass in the Lagrangian form, and then let's move on to the next lecture. In the next lecture, we talked about the momentum equation, where we have the material derivative of, well, we use this, discuss this expression on the material derivative for intensive property written per unit mass. And then we use that to write the linear momentum principle, which is basically the net external force acting on a collection of particles is the time rate change of the overall momenta of the system. So when you write that, again, I'll quickly browse through it because nobody had questions on this. That results in equation A, which is the linear, the local equation of motion in Eulerian form. And then when you apply the angular momentum principle, which says that the material derivative of the angular momentum about some point O is equal to the net torque or the moment of forces acting about the point O. Again, we assume the material to be non-polar, which is the case in almost all of the situations that we deal with. So for that, all this results in is the symmetricity of the Cauchy stress tensor sigma. So this is exactly what we had gotten earlier, but we have shown this for a general situation of accelerating material as well. So the material may not be in equilibrium, even then the sigma is symmetric. So I move on to the next lecture. So this was the Eulerian form. Now we in this lecture we talked about the Lagrangian form of the momentum equation, where we actually, this was a bit conceptual, where we said that although everything is, although the force balance was written in the current configuration, but we can define a traction vector such that it is the df upon d gamma naught. So rather than taking the ratio of the force to the d gamma, that is where how we define traction vector t. In this case, we take df to the d gamma naught, which is we track back in time the d gamma naught, which corresponds to this d gamma that we have in the current configuration. So this results in the traction vector, the stress vector t, which when expressed using the stress form results in the first Euler-Kirchhoff stress tensor that we call the capital P AI tensor. So again, I won't go into detail of that. That is something we discussed, and we actually saw that this, from the conservation of angular momentum principle, this was not symmetric. So this is the condition we got. So we saw that pk1 is not symmetric. But since we like symmetry, so what we said was, let's define another tensor S, capital S, AB, which is called the second Euler-Kirchhoff stress tensor pk2, which actually is symmetric. So by defining S using equation number m, we get a symmetric stress tensor, which is expressed in the Lagrangian form. Well, in terms of the material coordinates. So finally, we showed the relationship between the Euler-Kirchhoff stress tensors and the Cauchy stress tensor, and this is where we ended the discussion on this lecture. So next was a tutorial, but before the tutorial, we also discussed about the energy equation, a very brief discussion where we first wrote the law of conservation of energy, which states that if you, let's go to the right hand side first. So all the energies which are entering or leaving the body per unit time, uh, plus whatever rate of work is done by the different forces on the body, all that can do is it can either increase the internal energy, so that sort of you're storing that energy, or it can increase the kinetic energy of the system. The system may move faster. So this is what can happen because of all the energies entering or leaving, or the rate of work that is being done by different forces on the body. So if you express that in the mathematical form, this results in the energy equation, which is expressed here, which is also called the first law of thermodynamics. Right. So this is where, and then we had some problems where none of you had any questions. They were quite straightforward. So this sort of brings us to the end of this live session. I hope whatever, mainly the derivation that was a concern to a couple of you, has been clarified in this session. So in the next live session, which will happen in a week from now, we will be discussing the problems or the concerns you have, or the questions you have on constitutive models. And the last week, which is application, but I don't think anybody has much of a concern with the application part. So most of the questions are on constitutive models. So I thought of taking it next week. And if any other question is there regarding the previous weeks, that can also be discussed in the next week. So if in case you have something, please feel free to ask those questions in the Q&A session as you have been doing, or mention the question in the Google Sheet that was shared for the list of questions. Right. So please, I hope you're preparing well for the exam if you're registered for that. And thank you very much, and I'll see you next week.